Hi, my name is Angel Villar Corrales, and today I'm going to present MSPRED, video prediction at multiple spatiotemporal scales with hierarchical recurrent networks. This is joint work with my colleagues Annie Karapetian and Andreas Boltres and my supervisor, Professor Sven Bink. In this work, we address the task of future frame video prediction, which has a very simple definition. Given C consecutive video frames, denoted as seed or context frames, we want to generate the next possible N frames. And future frame video prediction has motivated by several applications, including enabling successful human robot collaboration, anticipative behavior planning in autonomous systems, or future frame video prediction can be used as a pretext task for self supervised representation learning. However, future frame video prediction models must overcome a set of challenges. First, the exact details in a video cannot be foreseen long into the future, thus making this task very complicated. For example, when a person is moving, it might not be possible to predict the exact position of the fingers, or in the autonomous driving scenario, it might not be able to foresee the exact position of the leaves in the trees around the roads. Second, due to the existence of multiple futures, frame predictions become blurry just at a handful of time steps. And finally, in robotic scenarios, frames are not the only interesting representation, but sometimes other representations, such as semantic segmentation, human poses, or trajectories, might be more relevant in order to make decisions based upon them. Existing models fail to overcome these three challenges, thus being limited for autonomous systems applications. In this work, we present MSPRED, which is a video prediction model able to predict future outcomes of different levels of abstraction at different timescales with distinct spatiotemporal resolution. An illustration of MSPRED is displayed in this figure. The core module in MSPRED is the hierarchical predictor, which is composed of three recurrent modules operating at different temporal resolutions. The lowest level processes all inputs and models the fast-changing features in the sequence, whereas higher levels, which operate with slower temporal resolutions, capture more abstract features that change slowly over time. In this slide, we have a more detailed representation of our MSPRED model. On the left-hand side, we have the input seed frames, which are fed through an encoder. The encoded features are given through the three levels of our hierarchical predictor in order to forecast these features into subsequent time steps. The predicted features are given to the decoder, which has three different decoder heads to simultaneously predict subsequent video frames and higher level representations, such as poses and locations with different spatiotemporal resolutions. The core module is the hierarchical predictor, which uses three different convolutional LSTMs operating at different temporal resolutions. The lowest level convolutional LSTM processes all inputs, whereas higher levels operate with higher periods, T1 and T2. The multi-head decoder is composed of three different decoder heads which operate with different spatiotemporal resolutions. Each head operates with the same frequency as the corresponding recurrent neural network, that is 1, T1, and T2 for the lowest level, intermediate level, and highest level respectively, and each head uses most recent feature maps from the current and above levels. Running the predictor model over time, we obtain the following representation, which depicts the flow of information in MSPRED. On the left-hand side, we have the seed stage, in which the seed frames are fed through the model, whereas on the right-hand side, we have the prediction stage, in which the features from the model are used to predict subsequent video frames and higher-level representations. During the seed stage, the seed frames are given through the encoder, and the encoded features are fed through the predictors. During the prediction stage, the predicted features are given to the decoder in order to decode subsequent video frames and higher-level representations. Note how each level in the hierarchical predictor uses a different temporal abstraction. The lowest level processes every input, the intermediate level processes one out of every two inputs, and the highest level in this case processes one out of every four inputs. MSPRED is trained to make 5 predictions on each level, which these correspond to the 5 subsequent video frames directly after the context frames, and in the higher levels, MSPRED makes 5 predictions using coarse temporal resolutions, thus being able to predict long into the future using just a handful of steps. Our model is trained by minimizing the following loss function. First, for each decoder head, we minimize a reconstruction error, which can be a mean squared error in the case of frames or heat maps or pixel-wise cross entropy for segmentation maps. Additionally, we enhance our model with a stochastic module, and additionally, we add a KL divergence loss into the final objective function. We perform experiments on 3 different datasets, which are quite diverse. including moving MNIST, KTH actions, and SIMPIC VP. These datasets and some statistics are shown in this slide. First, we perform an ablation study comparing different variants of MSPRED for future frame video prediction on the moving MNIST dataset. The results are shown on the table below. First, we know that the full MSPRED module, including a spatial and temporal hierarchy and supervision on the higher level decoder heads, achieves the best results, whereas removing some hierarchical component, that is the spatial hierarchy or the temporal hierarchy, significantly degrades the quality of the results. Second, we know that adding supervision to the higher level decoder heads is not a key factor of the success of our model, and our module trained only for subsequent frame video prediction achieves comparable results to the one trained for simultaneously video prediction and higher level prediction. We compare MSPRED with several existing video prediction models, including Trajectory GRU, SVG, PredRNN++, or FIDNet. MSPRED outperforms the existing video prediction models on the perceptual metric, that is LPIPS, on the three diverse datasets. On the moving MNIST dataset, all methods perform reasonably well due to the simplicity of the dataset. However, MSPRED is the only method which is able to make reasonable predictions when there's strong overlaps. On the KTH actions, MSPRED achieves the best results, whereas methods with high PSNR scores, such as ConvLSTM or Trajectory GRU, blur the image, especially around the arms and the legs of the person, or method achieves the best reconstructions. A similar observation can be seen in the SIMPIC VP dataset, in which MSPRED achieves the sharpest reconstructions, whereas other methods, such as ConvLSTM or Trajectory GRU, they blur moved objects and the robot gripper. Additionally, since our model simultaneously predicts subsequent video frames and higher level representations, we visualize the hierarchical predictions on the KTH and SIMPIC VP datasets. On the KTH actions dataset, our model predicts subsequent video frames on the lowest level, human poses in the intermediate level, and positions in the highest level using different temporal resolutions. We see how MSPRED is able to predict higher level representations long into the future using coarse temporal resolutions in just a handful of steps. On the SIMPIC VP dataset, MSPRED predicts subsequent video frames on the lowest level, semantic segmentation maps on the intermediate level, and the position of the robotic gripper on its highest level. In conclusion, in our work we present MSPRED, a video prediction model able to simultaneously predict future outcomes of different levels of abstraction with different spatiotemporal resolution, which includes subsequent video frames and abstract representations longer into the future using coarser temporal resolutions. MSPRED perceptually outperforms existing video prediction baselines while forecasting higher level representations such as human poses or semantics long into the future using coarse temporal resolutions. Future results and animations can be found in our project website. Additionally, in the spirit of reproducible research, we open source the codebase in order to reproduce the MSPRED experiments. Thanks a lot for watching.